Всем привет! Сегодня я читаю эту книгу, или лучше маню, если это слово. Называется... Что? xv6, a simple Unix-like teaching operating system. I actually already started a stream where I'm reading this, but I fell asleep. I was just like, for like an hour, so we're gonna restart. But I can talk a bit about my day. First off, Tamagotchi NVIM stars are going crazy. So I definitely want to work a bit on this as well. Just because it's not perfect yet. But work is being done to improve it. And give me about 20 more hours on that, and it'll work well. Currently, it works poorly. Yeah, it's good to see interest. Actually, as much interest as I've ever seen in a project I lead, which is quite crazy because the amount of work that goes into writing this is probably around 20 to 30x the amount of time that goes into running this. At least in terms of you can explain how to write Tamagotchi Envim in a minute. I can't even explain how to build this now. Probably take like 3 years to figure out how to build everything that needs to exist. So yeah, that's really interesting. But yeah, excuse me. So let's get the classic setup, mic in the middle. Just ignore this for now. Oh yeah, I will also likely. That is quite bugged. We're gonna likely be referencing the source on occasion. So yeah, let's just jump back into it. The shell calls main. I thought these were line numbers, but I don't know. I thought this was referencing some kind of marker in the source, but I don't believe that's the case. I don't. Certainly not a page number, be it 108 pages in the book. Oh yeah, I got into here. All right. Ladna. IO and file descriptors. Yeah, I had read this. This is like while I was falling asleep. So you can make pipes, sort of the everything is a file setup. File descriptor per process table. So every process has a private space of descriptor starting at 0. By convention, a process reads from file descriptor 0, standard in, writes to file descriptor 1, writes error to file descriptor 2, standard. So you'll see the shell exploits this convention to implement IO redirection and pipelines. Shell ensures that it always has those 3 file descriptors open, which are by default file descriptors for the console. Okay, so you can overwrite the FD0, FD1, FD2 to reroute standard error, standard in, and standard whatever one I didn't say. Probably standard error. So also let me just stream check. Did I actually start this? Okay, yes, it started. Yeah, we're chilling. Okay. The read and write system calls read bytes and write bytes, respectively, to open files. So you pass in the FD, the buff, and the length. Reads at most n bytes, copies them into a buff, and returns the number of buffs or bytes read. File descriptor that refers to a file has an offset associated with it. So I'm not sure that I knew this. Each file descriptor that refers to a file has an offset associated with it. Read reads data from the current file offset and then advances that offset by the number of bytes read. A subsequent read will read bytes. Oh, yeah, okay. Read bytes following the ones returned. Yes, indeed. There are no more bytes to read. Read returns 0. Signal EOF. The write call returns n bytes from above to the file descriptor MD and returns the number of bytes. Sorry, writes them, yes. Fewer than n bytes are written only when an error occurs, indeed. Like read, write, writes data at the end of the file, offset, number of ways each write picks up what the previous one left off. Indeed. The following program fragment, which forms the essence of the cat, copies data from its standard input to its standard output. If an error occurs, it writes a message to standard error. So we have a car buff 512 int n for, how would you say this? How do you pronounce? Oh my god. Oh my god, this is so annoying. This is honestly a Jippity question. Because Google search symbols is so clapped. Or some forever loop. Perhaps forever loop. I just say forever loop. I probably wouldn't. I don't know what I'd say to be honest. Okay. I'll probably keep that open in case I have another question. So and read buff size of buff. If n 0 break, if n greater, sorry, if n less, error. And then otherwise you just write. So I don't really like this control flow setup, but whatever. Important thing to note, cat doesn't know whether it's reading from a file console or pipe, and it doesn't matter. Close system call releases a file descriptor, making it free for reuse by a future open pipe or dupe. Newly allocated file descriptor is always the lowest numbered unused descriptor for the current process. Okay. File descriptors and fork interact to make IO redirection easy to implement. So I don't immediately see that, so let's read. Fork copies the parent's file descriptor table along with its memory. Oh, so that's, yeah, there was the pipe exercise where you had the, yeah, no, that's chill. Oh, that's actually dope. Yeah, okay. Fork copies the parent's file descriptor table along with its memory so that the child starts with exactly the same files as the parent. The system called exec replaces the calling process's memory. It preserves its file table. It replaces the calling process's memory? Yeah. Yes. Yeah, that's right. This behavior allows the shell to implement IO redirection by forking, reopening chosen file descriptors, and then executing your program. Type shit. Here's a simplified version of the code for a shell of the code. A shell runs for the command cat. You're directing input.txt into cat. So this is what the shell runs. argv2, argv0 is cat, argv1 is 0. If fork is equal to 0, close 0. So you're forking, and if it's 0, you're closing the so you're closing file descriptor 0. So you closed 0, and now you know when you open it'll be 0. Then exec cat is using 0. Huh, okay. That's kind of weird to me right now. Fork 0, then cat is grabbing. Huh, okay. That's kind of curious. Run command will call exec, so I know that. Why is it a good idea that fork and exec are separate calls? If they're separate, the shell can fork a child, use open close dupe in the child to change the standard input and output, and then exec. No changes to the program being exec are required. If fork and exec were combined into a single system call, some other more complex scheme would be required for the shell to redirect standard input and output, or the program itself would not understand how to redirect or. Yeah, that is a smart API. Can't lie to you. Although fork copies the file descriptor table, each underlying file offset is shared between a parent and child. Consider this example. So I just kind of read that without thinking. Although fork copies the file descriptor table, yes, each underlying file offset. Each underlying file offset is shared. Okay. It's shared. So what is meant by shared? All right, I guess it points to the same memory. So how does that work? Hmm. You inherit a copy of the descriptor table. So they're not synchronized and it's your problem to deal with it. Okay. I mean, I suppose that makes sense. Consider this. If fork is equal to 0, so it's evaluating this. So this is the child here. This is the parent. So the child will go here and the parent will go here. Right to a standard out. Hello. And 6. That's the length, yeah. Else wait. 8 world and 6. So you're waiting on the child. Okay, so it is synchronizing. File attached to the file descriptor 1 will contain the data hello world. The write in the parent, which thanks to rate runs only after the child is done, picks up. This behavior helps produce sequential output from sequences of shell commands like echo hello, echo world. Yeah, okay. The dupe syscall duplicates an existing file descriptor, returning a new one that refers to the same underlying IO object. Both file descriptors share an offset, just as the file descriptor is duplicated by fork do. This is another way to write hello world into a file. FD dupe 1, write 1, and FD, okay. So I don't really see the utility of dupe currently. Okay, so dupe allows shells to implement commands like this. OS existing file. I didn't even know that. I've never used that. OS existing file. Non-existing file. Into tempo 1. 2. Oh, I don't know what that is. 2 into and 1 tells the shell to give a command, a file descriptor 2 that is a duplicate of file descriptor 1. Okay. xv6 shell does not support IO redirection for the file error descriptor, but now you know how to implement it. So I don't really understand what ls with 2 arguments is. Yeah, I don't know that. But okay, I don't think it matters too much. Pipe, let's get to pipes. Small kernel buffer exposed to processes as a pair of file descriptors, one for reading and one for writing. Writing data to one end of the pipe makes that data available for reading can come from reading. Sorry, writing data to one end of the pipe makes that data. Okay, yeah, that makes sense. Makes that data available for reading from the other end of the pipe. Indeed, pipes provide a way for processes to communicate. Following example code runs program WC with standard input connected to the read end of the pipe. So int p2, argv, car pointer 2. So you have WC 0. Second time I've seen the argv1 0 and I didn't understand what it is. But okay. So where are we even using argv1? I guess it's just that it doesn't exist. Oh, because you have to, is this where you have to null terminate the last argument? I think that is the case. I believe that is the case, because yeah. Yeah, I did that. Indeed. Yeah, that makes sense. Pipe P. If fork is 0, so if we're in the child, close 0. So that means you're about to exec something. One sec. Type shit. All right. So yeah, close 0. So this is like we had to write this effectively. You close. I didn't use 0 because I had like a write. It was easier to see with a macro. But this is the if fork 0, you close this end. Or you're closing both ends. Okay. Wait, yeah, I don't really see this. WC and argv. Argv is still. So what do you work to? Hello world. You're putting hello world into P1. So let's read. Program calls pipe, which creates a new pipe and records the read and write file descriptors in the array P. So it's 0, 1, read, write. After fork, both parent and child have file descriptors referring to the pipe. The child dupes the read and dupes the read end. Yeah, so you close 0. So standard in. Oh, yeah. Oh, okay. You close 0, then put standard into the read end of the pipe. Closes them. Next, WC. When WC reads from its standard input, it reads from the pipe. The parent closes the read end of the pipe, writes to the right end of the pipe, closes the right side. So I'm not really sure why you need to close here. Let's ask. You need it to signal end of file to the child process. So yes, read and write end. When all file descriptors pointing to the right end of the pipe P1 are closed, the read end receives an end of file when all pipe data has been consumed. If the parent process doesn't close P0, it remains open in both the parent and the child. The child process, which execs WCV exec will attempt to read from pipe P0. It'll keep waiting. Okay. Okay, yeah, that's good. MWC, no data is available, read on the pipe. Either waits for data to be written or all file descriptors referring to the right end to be code. Close. In either case, read will return 0 just as if the end of the data file had been released. The fact that read blocks until it is impossible for new data to arrive is one reason that it's important for child to close the right end of the pipe before executing WC. If one of WC's file descriptors referred to the right end of the pipe, WC would never see end of file. If one of WC's file descriptors referred to the right end of the pipe, WC would never see the file. So it's setting standard out, standard in to the read end of the pipe, standard out to standard out. Yeah? I think that's right. Implements pipelines such as grep fork sh-c word count-l. Wait, just word count. Child process creates a pipe to connect the left end of the pipeline with the right end. And it calls fork and run command for the left end of the pipeline and fork and run command for the right end of the pipeline. And waits for both to finish. Yeah. The right end of the pipeline may be a command that itself includes a pipe. ABC works itself in a two-child process. I need some lotion, bro. The knuckles are clapped. Thus, the shell must create a tree of processes. The leaves of this tree are commands. And the interior nodes are processes that wait until the left and right children complete. The leaves of this tree are commands. The leaves of this tree are commands. Yeah. Yeah, that's true. And the interior nodes are processes. Okay. In principle, you could have the interior nodes run the left end of the pipeline. Doing so correctly would complicate the implementation. Pipes may seem no more powerful than temporary files. Pipeline echo hello world WC could be implemented without pipes as echo and to temp, word count to temp, or wouldn't that not be concurrent? Pipes had always 4 advantages. Automatically clean themselves up with the file direction a shell would have to carefully remove. Second, pipes can pass arbitrarily long stream of data, while the file redirection requires enough free space on distance around the data. Yeah. Third, pipes allow for parallel execution of pipeline stages. 4, file requires the first program to finish. So yeah. If you are implementing IPC, pipes blocking read and writes are more efficient than any non-blocking semantics of files. Okay. The file system. The xv6. I can't scoop, bruh. I can't scoop. The xv6 file system. I'm gonna just do my tour. The xv6 file system provides data files, which are uninterpreted byte arrays and directories. How did I not break something? By smashing my keyboard. and directories, which contain named references to data and other directories. Indeed. The directories form a tree. Zoning out a special dir called the root. Path like ABC refers to the file. Directory named C inside the directory B inside A, certainly. Paths that don't begin with a slash are relative. Indeed. Which can be changed with shader. Shader is, or okay, I guess if you want to do it within a program, okay. That's true. That's how I'm begin with that. Or evaluated relative. Yeah. You can change it with shader. Open the same file. Assuming all directories exist. Yeah, okay. All right, first fragment changes the processes. Yeah. What was this called to create a file or directory? Make dir, open with o create, make nod, creates a new device file. Illustrates all three. Make node permit makes a file in the file system with no contents. The file's metadata marks it as a device file and records the major and minor device numbers. The last two arguments to make node, which uniquely identify a kernel device. When a process later opens the file, the kernel diverts read and write system calls to the kernel device implementation instead of passing to the FS. Yeah, okay. fstat retrieves information about the object a file descriptor refers to. It fills in a struct stat, defines the stat.h as. Yeah, so I had that. uint. I had a lot of problems with the uint, but it was because I didn't realize that the ordering of your headers matters, which is quite elementary. Directory, file, and device. So you have a type. File systems, disk device. I'm surprised to see short int uint short uint. I'd expect to see like these shorts together. File's name is distinct from the file itself. The same underlying file called an inode can have multiple names called links. The link syscall creates another file name, system name, referring to the same inode as the existing file. This fragment creates a new file named both A and B. So syslink, yeah. Reading from or writing to A is the same as reading from or writing to B. Each inode is identified by a uke inode number. After the code sequence above it, is possible to determine that A and B both refer to the same array context by respecting the result of fstat and looking at the same inode number yet. The unlinked syscall removes a name. Furthermore, fd open unlink is an idiomatic way to create a temporary inode that will be cleaned up when the process closes or fd or exits. Yeah, I had to do that. Shell commands, file system operations are implemented as user level programs such as makedir, ln. What is ln? ln. What is ln? Link node? Link node? What is that? Design allows anyone to extend the shell with new user commands by just adding a new user program. In hindsight, this plan seems obvious, but other systems designed at the time of Unix often built such commands into the shell and built the shell into the kernel. Oh, I like the little gripper on it. That's kind of nice. Certainly. So one exception is CD, which is built into the shell. Yeah, because the parent's working directory would not change if you just forked it. Okay. Real world. That was a nice little conclusion there. Operating system organization. So we're already 20% done. The stream just started. Yeah, this is gonna be easy. Multiplexing, isolation, and interaction. This chapter provides an overview of how operating systems are organized to achieve these three requirements. Turns out that there are many ways to do so, but this text mostly focuses on mainstream design centered around a monolithic kernel. Oh, that's quite useful. All of the major abstractions that xv6 provides, how they interact, and how the three requirements of multiplexing, isolation, and interaction are met. Avoid special casing of the first process. Okay. Runs on Intel 80386 or later PC platform. Cool. Writing to a raw disk sector would be so cursed. User mode, kernel mode, and system calls. The int instruction. So mono with the kernel is that the operating system resides in the kernel, so that the implementations of all system calls run in kernel mode. Mm-hmm. Minimize the amount of operating system code that runs in kernel mode by making it a microkernel. OS services running as processes are called servers. So the shell via the microkernel sending messages to the file server. So xv6 is monolithic. Unit of isolation is a process. Prevents one process from wrecking or spying on another's process's memory, CPU, file descriptors, etc. It also prevents a process from wrecking the kernel itself, so that a process can subvert the kernel test version. Hardware page tables. Maps virtual to physical. Indeed. Instructions, global, stack, heap. Yep. So kernel mode is above 8,000. Or kernel mode is 1, starts with the leading 1. Which I'm surprised to see because it kind of wastes a lot of memory doing that because the kernel isn't that big. Half the memory is the kernel is kind of crazy. Each process's address space maps the kernel's instructions and data, as well as the user program's memory. Oh, okay, the text and data, user text and data. Wait, so how do I get out of grabber mode? No, how do I get out of grabber mode, bro? Wait, how do I get out of grabber mode? What is this? How do I get out of grabber mode to copy text? How was I copying text earlier? Process has two stacks, a user stack and a kernel stack. For syscalls or interrupt, it goes on the process kernel stack. Allocated, ready to run, running, waiting for IO, exiting. Zombie. Page dir holds a page table. Code. The first address space. The BIOS starts at 0. I guess so. 0 to 512 or whatever. What are these numbers? So you boot into real mode, yeah? Bootloader loads the kernel into memory at add physical address 1 zeros. The reason it doesn't load the kernel at 8010s is because there may not be any physical memory at such a high address on a small machine. 10 as opposed to all zeros is because the address range A000 to 10 contains IO devices. To allow the rest of the kernel to run, entry sets up a page table that maps virtual addresses starting at 10 called kern base, starting at kern base, to physical addresses starting at 0. Really, physical access is starting at 0, but I thought we just said 0 was for IO devices. I thought we just said that was IO devices. Oh, this is OS. Okay. So they're technically in the kernel space IO devices. Okay. Setting up two ranges of virtual addresses that map to the same physical memory range is a common use of page tables. What's the second page table? The entry page table is defined in main C. Look at the details of page tables in chapter 2, but the short story is that the entry 0 maps virtual addresses 0 to 04. So this is just one-to-one mapping that will eventually be removed. Entry 512. All right, so let me just look at main.c because I don't really understand what they're talking about. Main.c. Is he talking about line numbers? What is 512, dude? Switch not in here entirely. Kernel page table. The OSP is collapsed. Kernel restricted to 4 megabytes. Entry page dir is CR3. V2P, whoa. Subtracts current base in order to find out the physical address. Control registers here at 0. Has a bit set in it. Stack pointer ESP, point to memory to be used as a stack. Indirect jump is needed because the assembler would otherwise generate a PC relative direct jump, which would execute the low memory version of main. So how do you make the first process? alloc proc called for each process. User init only the first process. alloc proc scans the proc table for a slot with state unused. When it finds an unused slot, sets the state to embryo to mark it as used, and gives the process a unique PID. Next, it tries to allocate a kernel stack for the process's kernel thread. Memory allocation fails. Changes the state back to unused and returns 0 to signal failure. So that will probably be notable and unexpected when that comes. Let's see. So this is the kernel stack. You have a K stack, you have a context, all the registers. You have the top of the stack. Trap return. Address fork ret will return to is EIP or trap ret? Or in between them is, what does that say? Okay, now alloc must set up the new process's kernel stack. alloc is written so that it can be used by fork as well as when creating the first process. What time is it? I have a lot of other stuff I want to do tonight besides read this. Still got a few hours in this. Oof, it's already 9. Okay, we're not really making a lot of good progress here. Let me get my water. alloc must set up the new process's kernel stack. Excuse me. The kernel thread will start executing with register contents copied from pcontext. Thus, setting pcontext EIP to forkret will cause the kernel thread to execute at the start of the forkret. This function will return to whatever address is at the bottom of the stack. The context switch code sets the stack pointer to the point just beyond the end of pcontext. alloc_proc places pcontext on the stack and puts a pointer trapret just above it. This is where forkret will return. Trapret restores user registers from values. Okay, this is kind of a lot of ones. Trapret. So I don't really understand any of this, but I can't copy paste. 24. There we go. Can you explain this a bit? I read these sentences, but I don't understand what all the words do. Why certain things are limited at certain times. DC. So to create a process, you must allocate a slot in the process table. Allocate a kernel stack for the process. Real quick, why does a process need a kernel stack? When a process requests a service from the kernel, like reading a file, it transitions from user mode to kernel mode. Kernel stack stores function call names, local variables, and arguments during this execution. No, that's not true. Okay. Yeah, okay. Then here, so let's see. Struct process in the process table. State, kernel stack, registers, memory space, etc. So context is the register context. Okay. K stack is the kernel stack. So in kernel stack, it says calls trapret is a function that restores user space for registers and jumps to the processes. Okay. Forkret executed first when a new process starts running. Performs housekeeping tasks. So alloc_proc. Allocate process slot. So the process table has a max. alloc_proc scans for one that's unused. Marking the slot as used, set it to an embryo, indicate that it's been set up for any process, unique PID is assigned. Okay, yeah. Kernel stack allocation. Kernel allocates memory for the process's kernel stack. Stack is used for handling syscalls, interrupts, and other activities. Allocation fails, it's reverted to unused. Kernel stack is initialized with a specific layout so that when the process starts, it knows where to begin executing. Return program counter is EIP. Sets EIP to point to fork rep. This means that when the process runs for the first time, it executes the fork rep. Trap rep. Okay, so it's the memory address of the next instruction. Extended instruction pointer. So the setup, process starts running, it has fork ret, which sets stuff up at some capacity. So after fork ret, you return, which pops the next address from the stack into EIP, and now you're doing trap ret. It's the second function. Okay. Yeah, I didn't necessarily, I didn't really mean instruction. Okay, that's kind of dope. Trap ret restores values. Jumps into the process. And all of that was talking about the kernel stack, yeah. Yeah. Okay. Я понимаю. Ладно. All right, so I might not read this whole thing tonight. I actually might stop after this chapter. Whenever control transfers into the kernel while a process is running, the hardware and xv6 trap intercode save users as on the processor's kernel stack. User init, which is the first user process, writes values at the top of the new stack that just look just like those that would be there if the process in the kernel were interrupt. So the ordinary code for returning from the kernel back to the process's user code will work. So it kind of artificially acts like it's been execs, even though it hasn't been, just so that you can actually go back to it. syscalls, interrupts, exceptions. Hardware saves the key user mode registers onto the kernel stack. When user init creates the very first process, there hasn't been any actual transition. However, the kernel stack for the process needs to look like the process entered the kernel via interrupt. Okay. So you need to be able to return back from the kernel to the user mode. Okay. And so you don't have to have a special case. Okay, that's kind of dope actually. So the first process executes a small program. Process needs physical memory in which to store this program. Program needs to be copied to that memory. Process needs a page table that maps user space addresses to that memory. User init calls setup KVM, setup kernel virtual memory, to create a page table for the process with at first mappings only for memory that the kernel uses. We'll study this function in detail in chapter 2, but at a high level, setup KVM and user init create an address space as shown in figure 1-2. So that's from like way back up. The initial contents of the first process's user space memory are the compiled form of init code.s. As part of the kernel build processes, the linker embeds a binary in the kernel and defines two special symbols: binary init code start and binary init code size, indicating the location size of the binary. User init copies that binary into the new process's memory by calling init UVM. Ah, okay, so it builds all the binaries. That's kind of smart. That's kind of cool, actually. I didn't. That definitely makes sense. I just didn't realize that's what was going on in Civil. Yeah. User init copies a binary into the new process memory by calling it UVM, which allocates one page physical memory. Maps virtual address 0 to that memory and copies the binary to the page. Then user init sets up the trap frame of the initial user init state. CS register contains a user segment selector for the code segment running at a privileged DPR user. So user instead of kernel. Similar DSESS use seg udata with privileged DPR user. The eflags FOIF bit is set to allow hardware interrupts. We'll examine this in chapter 3. Stack pointer ESP, extended stack pointer, is set to the process's largest value's virtual address. Of course, PSZ. The instruction pointer is set to the entry point for the init code address 0. The function user init sets p name to init code manually for debugging. Setting pcwd changes the process's current working directory. We will examine the name in detail in chapter 6. Once process is initialized, user init marks it as available for scheduling by setting the p state to run. Now that the user's first process state is prepared, time to run it. Main calls user init. MP main calls scheduler to start running processes. Scheduler looks for a process with p state set to runnable. And there's only one. Sets the per CPU variable proc for the process it found. And calls switch UVM to tell the hardware to start using the target process page table. Changing page tables while executing in the kernel works because setup KVM causes all processes page tables to have identical mappings for kernel code and data. Changing page tables while executing in the kernel works because setup kernel virtual memory causes all processes page tables to have identical mappings for kernel code and data. Okay. So they're mapping to the same kernel. Switch v UVM also sets up a task state segment seg TSS, instructs the hardware to execute system calls and interrupts in the process's kernel stack. We'll examine the test case segment in chapter 3. Scheduler now sets p state to running and calls switch to perform a context switch to the target process's kernel thread. Switch first saves the current registers. Current context is not a process, but rather a special special per CPU scheduler context. So scheduler tells switch to save the current hardware registers in per CPU storage, CPU scheduler, rather than in any process's kernel thread context. Switch then loads save registers of target kernel thread p context into the x86 software registers, into the x86 hardware registers, including the stack pointer and instruction pointer.
We'll examine switch in more detail in chapter 5. The final ret instruction pops the target process's EIP from the stack. Okay, finishing the context switch. Now the processor is running on the kernel stack of process P. Hmm. Hmm.
The speed on that is wild. Like literally instantaneous. That's quite impressive. I wonder if when you paste it in before you press enter, they're already computing something. Because that was just insane. During a context switch, oh, of course, you have to load this kernel context. Yeah, okay. Fork ret runs initialization functions that cannot be run from main because they must be run in the context of a regular process with its own kernel stack. Fork ret returns, remains the top word on the stack after p context is passed off will be trap ret. Now trap ret begins executing with stack pointer set to tf trap frame. Uses pop instructions to restore registers from the trap frame just to switch to the kernel context. So yeah, restoring registers. Oh, that's kind of dope. Popl restores general registers. Popl restores S registers. Addl skips over the two fields, trap, no, and error code. Finally, the iret instruction pop CS. See from the stack. Contents of the trap frame have been transferred to the CPU state. So the processor continues at the EIP specified in the trap frame. For init proc, that means virtual address 0. First instruction of initcode.s. At this point, EIP holds 0 and ESP holds 4096, so this is one page. These are virtual addresses in the process's address space. Paging hardware translates them into physical addresses. alloc UVM is set up to process's page table so that virtual address 0 points to physical memory allocated for this process. Instead of like GTU that tells the paging hardware to allow user code to access that memory. The fact that user init set up the low bits of CS during the process's user code at CPO3 means that the user code can only use pages with PTU set. It cannot modify sensitive hardware registers such as CR3. The process is constrained to only using its own memory. Okay, we're close. First, syscall exec. Now that we have seen how the kernel provides strong isolation for processes, let's go to your process and re-enters the kernel task for services that it cannot perform itself. First action of initcode S is to invoke the exec syscall. As we saw in chapter 0, exec replaces the memory and registers of the current process with a new program, but it leaves the file descriptors, process ID, and parent process unchanged. Initcode S begins by pushing 3 values onto the stack, argv, init, and 0. It notes that's EAX to sysexec and executes tsyscall. It's asking the kernel to run the exec syscall. Makes sense. If all goes well, exec never returns. It starts running the program named by init. Oh, okay, yeah. Which is a pointer to the no terminated string /init. So that's somewhere in the other argument is the argv array of command line items. The 0 at the end of the ring marks its end. If the exec fails and does return, init code loops. Wait. And then you have an argc with 0. What happens if you do? How does that work? Dope.
A real operating system would find free proc structures within explicit free rest and constant time instead of the linear search and alloc proc. All right, so I might just end it there, being like a fourth of the way done. Just a short hour stream, but I want to work a bit on game dev.
All right, yeah, so I'm gonna get on my laptop, and so yeah, sadly. Oh wait, can you actually read? Dude, I love Sway VM, bro. No, I love Sway VM. Oh, this certainly wasn't programming. This was research. Reading. So yeah. So I think I'm gonna end it. Yeah. I'm looking forward to my operating system class. Actually, I will probably try and be a TA, just because I want to have been a TA for one time. I can't be a TA for compilers because I'll graduate. I'll graduate next semester, but it's only offered in the spring. And I honestly don't. I'm not really enjoying the class too much. I think that I don't know what I enjoy about compilers. It's not that I enjoy compilers. It's that I enjoy programming languages, I guess. In that I more enjoy front ends. I'm not. I don't care too much about optimization algorithms, like all these control flow graph algorithms. It's not really my interest. I more enjoy the language constructs and even like the dev tooling, like the OSP. And that's, I mean, you can kind of see that in the issues that I take and glean. Like, I mean, for one, there's not really a middle in, and that is just compiling to Erlang source. But if I was to make a programming language, I would certainly be I would be quicker to make a programming language that compiles to C or to GHC core. That would be kind of dope, actually. That'd be kind of dope. That'd be kind of cool, actually. But I would be quicker to do that than write a middle end. I mean, certainly there's kind of a monopoly on middle ends. That's not the case on front ends, which is one practical case to be more interested or particularly disinterested in them. Yeah, I don't really know what I was trying to say with that. I'll finish the rest of xv6 another time. Sure, I could have finished it now, but a lot of the content will also maybe be useful if I don't learn it until it's also covered in lecture, just for some temporal locality, perhaps. But yeah, I'm gonna work a bit on the game dev project. I also need to start working on Funtension as well, because not even in the sense that I need to churn out a lot of features, I just need to figure out how I'm gonna get people interested in the project. Because even if I did fully try, like, work a bit more than I'm comfortable working on it, which would be quite a lot of time, I don't think it would see success. Just, I mean, this is a type of project that takes people that know what they're doing a long time to write. Like, I mean, a good one is written over years, perhaps. So, by multiple people. So, perhaps it'll be reasonable, or I mean, it's certainly reasonable to cap the features, such as maybe we just implement an order book, or we copy a bunch of other stuff. Perhaps it's more of an assistant to a more software-oriented trading setup. It could just be, I mean, at the end of the day, we could just write a network card. I'll consider that. I should need to consider that quite soon. But yeah, that's all.